Good afternoon and welcome to today's webcast, Spacer Cable Systems, Best Practices for Longevity, presented and sponsored by Marmon Utility, LLC. My name is Mike Albrecht. I'm your moderator for today's webcast. Before we begin, let me explain how you can participate in today's presentation. First, if at any time you have audio difficulties or slides are not advancing, simply hit your F5 key. Again, that's F as in Frank, the F5 key to refresh your webcast console. If you have any technical difficulties during today's session, please press the Help button on your player console to receive assistance in solving common issues. This webinar technology allows you to resize the presentation by clicking the Maximize icon in the upper right, or by dragging the lower right corner to enlarge the window. We welcome your questions during today's event. In order to submit your questions to today's presenter, please simply type your question into the question window on the left side of your screen and then hit the Submit button. We'll be answering as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time and we'll add them to the queue. Please also be aware that today's session is being recorded and will be available within the next day for you to review. You'll be notified by email when the archive is available. Brian J. Trager is a member of IEEE. He received his Bachelor's in Engineering and Master's of Engineering degrees in Electric Power Engineering from Rensselaer Polytechnic Institute in New York in 1978 and 1980, respectively, and a master's degree in business administration from the University of Pittsburgh in 1986. Mr. Trager has held various positions in engineering, consulting, and management at American Electric Power Company, Cooper Power Systems, and Fisher Pierce, and most recently at Hendrix Wire and Cable, where he is currently employed as Director, Technology and International. He has taught electric power engineering at Ohio State University, West Virginia University, and Pennsylvania State University, in addition to teaching courses to utility clients, and has authored over 50 technical papers and articles for the IEEE and other national and international organizations. With regards to electric power line specification, design, construction, and management, Mr. Trager has worked on projects funded by international aid organizations, including USAID, ADB, JBIC, and others, to meet growing demand worldwide through the expansion of electric power infrastructure. He has brought to fruition numerous high-reliability power distribution projects in various sites on 7 continents over a period spanning 39 years, and for the past 24 years, solely dedicated to the aerial covered connector conductor systems. Excuse me. Now over to our presenter. Brian, the floor is yours.
Thank you for that, very much for the introduction, Michael. And I'd also like to thank T&D World for sponsoring this webinar, and certainly for all the viewers who took time from their busy schedules to join us today. So without further ado, the topic here is Spacer Cable Systems Design and Construction Best Practices for Longevity. The overview is going to give a quick introduction. For those of you who are not entirely familiar with the system, we'll talk about theory of operation. Then we'll briefly discuss engineering considerations, most importantly application categories, get into best practices, and I'd like to finish just ever so briefly with talking about what's happening in the industry. Do we have any innovations? And if we do, what they are. People say, hey, is this a new technology? And the answer is no. It's been around since 1951. We've got almost 7 decades in this technology. We started out at 5 and 15 kV, quickly went to 25, 35, and 46 kV, and then 69 kV we introduced in the 90s. We've got over 25 years with 69 kV. The next step will be 115 kV. And hopefully we'll see that within the year. We're in over all 7 continents, over 75 countries. We have continuous development, R&D development in this technology, and we're using it for reliability, economics, and safety. And I say lastly that it's a design option. It's not intended to completely replace underground or overhead. We're going to use it where we have the best reliability, economics, and safety justifications, where we have the best value proposition for a given application or utility. If we look at the system itself, spacer cable is heavily covered non-shielded phase conductors, and they are held together and supported by a high-strength messenger cable. That messenger has 4 functions. It's the mechanical support member. It holds everything up in the air. It's the system neutral for systems connected in Y. It's a lightning shield, and mechanically, it holds everything off of that system that may fall onto it from above. You can see we've got a diamond-shaped spacer there at the pole. We have spacers every 30 feet. And lastly, we have a couple of brackets, tangent bracket, dead-end bracket, angle bracket, and that's it. It's a very simple system. We're covered by National Electric Safety Code that says essentially if you have a good insulation on that conductor, you can move those phase conductors closer together. It doesn't say how close we can move those phase conductors together. Hendrix has made that definition, but it says indeed we can move those closer together, but we must respect all other clearances to ground, to wall, to boat ramps, to bridges, et cetera, et cetera, et cetera. There is a caveat. There is a change in National Electric Safety Code for one of those clearances, and I'll discuss that in a few slides down the road. If we want to briefly explore the theory of operation, if we take a look at a bare wire system, we use essentially air as the insulation. Air is a halfway decent insulator. But as it turns out, you need a whole bunch of it, so those phase conductors have to be pretty far apart. And that system is still subject to outages due to contact with trees, due to contacts with animals, and then due to contacts with conductor clashing and flashover and lightning events. So what we do is we put some polyethylene on those bare conductors, and that polyethylene as an insulator replaces most of the air and allows us to bring those phase conductors closer together. That polyethylene gives us a high BIL, gives us a high 60 Hertz withstand, and now those phase conductors are able to withstand short-term phase-to-phase contact, phase-to-ground contact, phase to what have you, trees, animals, et cetera, without suffering a fault. Our design objective is that, in general, we try to limit that charging current on the surface at 15 kV to 1/3 of a milliamp, so 350 microamps, so 1/3 of a milliamp. So to put that into perspective, we need, say, 7 to 10 milliamps to fibrillate the human heart. So 1/3 of a milliamp, we've got about 5% of the fibrillation threshold. So is it dangerous? Yes. Is it fatal? No. And that 1/3 of a milliamp on the jacket allows momentary contact without an outage, and it's not going to damage the insulation over the useful service life of the conductor, which is of tantamount importance for a long, useful service life. The construction basically consists of 3 layers. We first use a semicon over the bare conductor. The semicon smooths out the electric fields when we're in contact with the ground plane. The inner dielectric is a soft, high molecular weight polyethylene that has a great BIL and AC withstand voltage. And importantly also, it's very soft, so that when we do cable stripping it makes it much easier to strip that jacket to make taps. Lastly, the outer jacket is going to be a high-density polyethylene. It's the highest density polyethylene we can source, with the anticipation that we need a very high abrasion resistance should we ever come into contact with trees. It's also where we're putting our UV inhibitor and our track resistant adder. And the thickness of that covering obviously is going to depend on the system voltage. Due to Ohm's law, if we have more voltage, we're going to need more impedance to limit that charging current on the surface. If we go into engineering considerations, there are a couple that jump right out at you. The first is improved voltage regulation. We're going to have 15 to 20% better voltage regulation when we compare this to a bare wire system. We're going to have a very high BIL. We talked about security and safety. No energized conductor is ever safe, but this will give you a shock. It's not fatal, so it's safer, a million times safer than bare wire lines. It's going to be low profile, which means I can use shorter poles, less visual impact. I can build multiple circuits, restricted right-of-way construction, and NESC compliance. Again, this material is going to be available after the webinar. People always say, I just don't understand this whole concept of better voltage regulation. Why do I get a better voltage regulation when I have the same size conductors that are using spacer cable instead of bare wire in an open construction? These are the formulas I put down here that explain it. Essentially, the formula that says log of GMD on GMR for the inductive reactive parts of that impedance. As the geometric mean distance decreases, the geometric mean distance is the cube root of the triple product of the interphase spacings. As that decreases, as those phase conductors come closer together, that geometric mean distance decreases, the mutual inductance decreases, and the total impedance decreases by 15 to 20%. So if we look at that summary, the spacer cable is going to give you 15 to 20% better voltage drop than bare wire or tree wire. It's going to have a better 15 to 20% better end-of-line voltage on any feeder, but certainly on voltage-limited feeders. It's going to have a higher power factor. The X on R ratio of a spacer cable line is closer to underground cable than it is to bare wire. And we'll probably still use reactive compensation, switch cap banks, but they're going to come on a lot less than bare wire or tree wire. And same thing, we'll still have voltage regulators at the sub, but they're going to be operating less frequently. Here's the BIL. If you look here at 150 mils, that's going to be a 15 kV system. So that cable, we'll give that cable about a 200 kV BIL. The system BIL, once I put the spacer in there, is going to be in excess of 300, 350 kV. And if we use a larger spacer, you can have, 300, 400, 500, 600 kV BIL. So it's really shockingly high BIL system. And here's for the 15, 25, 35, and 46 kV systems. Let's take a look at the major application categories. Obviously, the biggest one for spacer cable is reliability. We are going to completely eliminate temporary faults, no more. Permanent faults, it depends, we're going to probably mostly eliminate permanent faults, but it always depends on what hits the pole. Severe weather, we're great in wind, ice, and snow. Hurricanes, we're not going to have any galloping anymore for ice or wind-induced galloping because essentially we have a vibration damper every 30 feet, which is the spacer. In tree-related applications, we're going to have 80% reduced tree trimming. We're going to save about 80% of that canopy, vastly improved aesthetics, vastly improved public relations, vastly improved economics because we're saving 80% of the tree trimming budget, and you can see the tree trimming budgets at the utilities across across North America, just absolutely staggering in the dollar value. So saving 80% of the tree trimming budget on spacer cable circuits is a lot of money. And you're also saving money by not sending crews out at midnight on Saturday night to put lines back in service. And lastly, in that tree-related applications category, I put national parks and recreation areas because we're doing national parks projects all over the U.S. and Canada, Mexico, and South America, and as far away as New Zealand and Australia and Japan, other countries as well. This shows just a couple of slides. Again, we have thousands of these slides. The photo on the left shows a palm frond down over a spacer cable line. That's not going to cause an outage. It's not going to cause a problem. You're going to get that on an annual patrol, hopefully knock it off with a hot stick. If you look at the bottom right photo, this is the Panama Canal zone. We're all along the canal, and that's a 35 kV, 34.5 kV transmission line. And there's a lot of concern here for reliability to keep the irrigation pumps on for the canal. Also concern for birds and tree monkeys and these types of animals that cause outages on bare wire systems, not to mention respect for the animals themselves. Two other categories that have come up is one's called storm hardening. The next is wildfire mitigation. So storm hardening. It's interesting when you look into. I know a lot of the big utilities have storm hardening programs, especially after being hit by massive hurricanes. It's important to harden the system before the storm, not after the storm. Be proactive about it. Standard techniques, if you look at the literature, the first one is pole inspection, pole upgrade, selective undergrounding, put underground cable in places where you think it will do you the best. And the third category is distribution automation or smart grid. So obviously automating the distribution system will help get you back online faster in the event of a major outage. But as a colleague said at a recent conference, don't build your smart grid on a house of cards. A storm-hardened system will be less likely to suffer an outage in the first place. However, automating a weak, vulnerable system is a misdirection of resources. So again, harden your system before automating it. And spacer cable is a solution in this regard. And again, we've got tons of these kinds of photos. You can see on the left, an ice storm has taken a massive treetop and busted it down over the power line. Spacer cable just sits there and takes it. No outage. Just wait until the crews get out there and remove that big tree. You see the photo on the right is the famous ice storm of 2008 that we had in the tri-state area here in New England. We had a lot of testimonies. We wrote an article about this in a technical paper, and a lot of these spacer cable circuits survived. And as I said, we're on all 7 continents. The power system, the medium voltage system on Antarctica is spacer cable, and that's been in since the 70s, and that's operated like a champ. So we've completely eliminated temporary faults. How about permanent faults? Here we can see this is suburban New York, Freeport, New York to be exact. This is a typical last week of October, first week of November photo. It's raining every day, end of hurricane season. The leaves are off the trees. You can see this tree has been blown down by high winds. It's smashed into the pole on the opposite side of the street. It's broken everything on the pole. You can see the luminaires on the ground. But if you check closely, you can see that tree is sitting on the messenger connected to the pole on the right. And out of the picture on the left, it's connected to the pole on the left. The linemen come out. They cut that tree tiny piece by tiny piece so as to not suffer a violent swing of the messenger, creating a safety problem. They've straightened out that pole. They put a new bracket on that pole. And with the equipment handler on the bucket, on that truck, they've lifted that bundle up by the messenger, put it in the parallel groove clamp on the tangent bracket, turn the bolt, and they've never had an outage. And this single photograph is the most powerful value presentation for spacer cable, why utilities are using spacer cable. It's all about safety and SAIDI. And again, we've got tons of these photos. This is another one of New Brunswick Power. This tree stayed on this line for 2 years. Yes, there was some damage. They never had an outage. We had to go in and talk about maintenance programs. You know, when you do your annual patrol, if you see a line, a tree on the line, please take it off. This is a 69 kV line in Washington, D.C. at PEPCO, where we have several of these 69 kV systems. Helicopter Patrol got this. They sent the crew out. They looked at it. There was no outage. The tree had obviously been there for a couple of months, and they took it down. If this was bare wire, everything would have been on the ground. And this is the best photo we have of trees on a line. This is in Banff, in the Northern Rockies in Alberta, Canada, and you can see on a single span, this is spring patrol. The linemen go out there, and you can see on a single span, you can see one far back, two in the middle, and the third one. There's 3 trees lying on this messenger without an outage. Tree trimming comparison, bare wire on the left, massive donut, tree massacred, spacer cable on the right. You know, this is the new philosophy. This is the new environmental stewardship philosophy. You're building your power lines under the major trees. You're letting those trees grow up and over the road. You're minimizing or nullifying the tree trimming. You have fantastic reliability. You're not killing birds, animals, squirrels. There's shade over the trees. You're blocking the wind from the houses. It's just the new environmental paradigm for power line construction. Wildfire mitigation. This is the new system hardening. Wildfire mitigation, relatively, you know, something that we've only seen in the last 5 or so years. There's tons of information of this on the internet. You know, the average economic loss due to wildfires is from '84 to 2013 per event is 275 for the U.S. and 325 for Canada. That's a shocking amount of money. We had a single fire in Colorado that cost about $450 million. There's stuff in the literature said the California Commission is adopting new regulations, a new policy, including significant new fire rules for utility poles and wires. So how do power lines cause wildfires? Essentially, lines blowing into trees during the high wind events. You think of down lines, 30% of the cases where the conductor hits the ground are what's known as high impedance faults. There's not enough impedance to get enough current to get a fuse or circuit breaker to trip. They commonly remain on that ground until reported by a homeowner. And sometimes, by the time it's reported, it's created a wildfire, and in many cases that's too late. Other reasons, conductor clashing. Sometimes 2 conductors slap together in high winds, and that high energy arc and particles are ejected, they cause a wildfire. Or fault-induced conductor slap. There's a fault on one side of the system that creates high surges in the phase conductors that cause them, by virtue of their magnetic fields, to either separate or go together, slap, conductor clashing, throw hot particles down into the weeds. And vegetation contract, the branch goes over 2 phases, eventually goes on fire, falls to the ground, and creates a wildfire. And then the Mylar balloons, which is, to me, it's absolutely mind-boggling. These apparently are causing all kinds of havoc in the western part of the country. People have parties, I don't know, birthday parties or anniversary parties or whatever, and the balloons get away, they go up, they get caught in the power lines, have a metal balloon bridge to energized conductors, boom, and you've got yourself a fire. So this is unbelievable, but it does happen. There's tons of this stuff on the internet. So the objective, eliminate possibility of wildfire being caused by an electric power line. And how does covered conductor spacer cable meet that objective of preventing wildfires? Essentially, conductor clashing, vegetation contact, or wind-blown lines do not result in flames nor sparks being thrown down onto the dry brush and igniting. Real quickly, we'll talk about right-of-way limitations. We really don't have enough space to build a power line. And this might be in a commercial alleyway, it might be in a residential alleyway, it might be residential backlot construction that we have quite a bit of here in the U.S. Road widening projects where we've run out of space on the side, and long spans. So if we've got tight alleyways or building clearances where we really don't have enough space, National Electric Safety Code modified Rule 234 in 1987. That rule requires 7.5 feet to the building side for a bare wire construction. Now it allows 2 feet less when using a proper covered conductor, so 5.5 feet. So this is a typical project you would have in a 5 to 15 or a 5 to 25 or whatever voltage upgrade in an alley. So if I needed 7.5 feet for bare wire, it wouldn't fit. So I'd only be able to go underground, which is always a good option, but sometimes a little bit expensive, or bare wire, which NESC says I need to be 14 feet above the rooftop. And that's, while it's doable, 14 feet above the rooftop creates safety hazards for painters and workmen on working personnel on those roofs. So you can fit a spacer cable system here very nicely, save a bundle of money, and be NESC compliant. And this is the type of projects we're doing. There's the 15 kV rat's nest, if you will. Again, I can go underground, but that's expensive. There's all kinds of utilities down there. I can go over the roof with bare wire, 14 feet above the roof, but that creates a safety hazard. Or I can simply go with spacer cable. And that's what it looks like. Alleyway construction, again, this is a triple circuit substation exit going down a residential alley, just 2 or 3 blocks, and this is instead of going a half mile down the street, 2 or 3 blocks over and a half mile back, so they saved a fortune with this application. And we have a lot of these applications where we're close to the buildings. Do a lot of this in the U.S., downtown areas of a lot of munis and co-ops, and this happens to be in Mexico where they put a second story on this house, and it just was too darn close for bare wire. It was an accident waiting to happen, so that was converted to spacer cable. Do a lot of long spans and river crossings. It's a simple application. This is Massachusetts, 200-meter crossing, and also a seacoast application. Here's a triple circuit in New Brunswick, and this is 520-meter, 1,600-foot river crossing in Indiana, and the other options were either submarine cable, which cost a lot of money, or building around the shoreline, which would have cost also a lot of money. So this was a massive savings, just building a spacer cable line. Multiple circuits, there's really no limit to the number of circuits you can get on a pole, whether you're doing a transmission line underbuild. Okay, transmission line underbuild, distribution line overbuild, or a substation exit. Here you can see we've got a high voltage transmission line, and it's no problem getting 2 35 kV circuits beneath the transmission structures, and it's also no problem building those long spans. Here's 4 circuits on a pole, 15 kV. This is a co-op in Northern Virginia. This is a pretty common construction type to put 4 circuits on a pole. And again, as I said before, there's no limitation whatsoever on the number of circuits on a pole. I can show you photos of 9 circuits on a pole. So we've done a lot of really high density renewable energy projects with spacer cable. Lastly, environmental stewardship. we are saving, again, 80% of our tree trimming. So we're coexisting with trees, we're preserving wildlife and migratory bird species, and electromagnetic fields are vastly reduced for anybody that still matters to. Here's a photo of, again, as I said, we're doing a lot of national parks. Here's a 69 kV system in South America in one of the famous national parks in the south of Chile, and it has a 25 kV underbuild, and that's a ring line around the city of Pucón in Chile. Here's a nice photo. There's a national wildlife refuge we did in the state of California, Tule Lake, and as soon as we finished it, the bald eagle was gracious enough to land for a photo. As I said, we're doing a lot of UNESCO World Heritage Sites around the world. We're proud to have build these lines in the Galapagos Islands to save some very darn important migratory bird species, and as well as New Zealand. We're in a national park there on the South Island, and there's a 35 kV line. And again, the photos just keep coming. Engineering managers and people send us these photos from all over the world. This is an interesting photo of a three-toed sloth in Costa Rica. I have it on good news that he made it. So they were called, they took the photos, but he was okay. No doubt he's getting, I would say, 1/3 of a milliamp over here since he's hanging on the messenger. He's touching the phase conductor, but I don't know if he's too furry to get the full 1/3 of a milliamp, but he seemed relatively unfazed. So we'll move on to best practices. I did something different this time. I posed the best practices as a series of questions that clients always ask us, and I tried to prioritize those questions. So, and I maybe put in the top dozen of those questions. So the first one is, why the need for polymer insulators and covered tie wire? It has to do with dielectric incompatibility. Dielectric incompatibility refers to the use of dielectrically incompatible components, in this case using polyethylene covered conductor with porcelain insulators or with porcelain spacers. I don't know if anybody sitting in today is old enough to have ever seen a porcelain spacer, but in the Stone Age we had them, and yes, most of them have been removed. But you can see dielectric incompatibility. We've got a covered conductor with a dielectric constant of 2.3 sitting on a porcelain insulator with a dielectric constant of between 8 and 9. Only poly insulators and spacers should be used with covered conductor. Porcelain has a higher dielectric constant, so the cable covering shares a much higher portion of that voltage drop. Again, between that bare conductor and the ground, it's a voltage divider circuit, and it's going to divide in inverse proportion to the dielectric constants. So this disproportionate sharing of that voltage drop is going to cause cracking and erosion and lead to eventual failure. It can be problematic at 15 kV, but it can be more serious at 25, and at 35 kV it can cause a failure within 6 months. And there's what that failure looks like. You can see this top, the cable on the top insulator is blown. If you take a look at the right insulator, you can see that there's tracking and cracking there due to that partial discharge. So the damaged cable leading to a failure is not a matter of if, but simply a matter of when. It will eventually fail, give it enough time. More troubling in my mind is the effect on safety. Again, as I start creating partial discharge through dielectric incompatibility, I'm eroding that insulation. I'm decreasing its insulation characteristics. I'm increasing the amount of current that's on the surface, and that's going to pose a safety issue for linemen and citizens should they come in contact. Why do I need covered tie wire? Well, the use of bare wire creates an air gap between the tie wire and the cable. The air gap itself is a capacitor. Air is a capacitive material. The cable is at line voltage, while a tie wire may be at a slightly low voltage. If and when this voltage difference is great enough, as in the case when the cable is in contact with a tree, there'll be a capacitive discharge across that air gap, also known as partial discharge. This PD can cause damage to the cable covering. Any damage which reduces the insulation thickness, surface continuity, hydrophobicity, integrity, etc., is going to be undesirable. So putting a coating on that tie wire, whether that's a flexible thermoplastic rubber, ensures that it will remain a floating electrode and be isolated from outside grounding influences, you know, if we're in contact, say, with wet leaves. How about poly tie wire on the insulators? Polyethylene tie wire was introduced in the U.S. probably 30 years ago. We finally got figured out it wasn't working. I've still seen some of it in other countries, so it's still being used. So poly tie wires introduced to date have been extrusion molded. Obviously, how else are you going to make them? So with parts this thin, it's impossible to get uniform UV inhibitors mixed into the base resin. So the result is I'm going to have UV degradation, premature aging, eventual failure. They're going to fail mechanically. So conclusion is use covered tie wire. It's simple. Or better yet, use vice-top insulators. So the top left here, you can see a poly insulator, covered conductor, covered tie wire. Life is simple. In the bottom right, you see a vice-top insulator. The benefits there are basically I'm not even using a tie wire. Just put it in the center there or the side, close the two screws, and you're done. And the linemen love this. It's very simple, cheap, and effective. This is the biggest one, I think. You know, people say, well, why not just strip the conductor at the porcelain insulator and put my conductor there? Okay, so essentially the industry discovered dielectric incompatibility in the 60s when failures started popping up at porcelain insulators and porcelain spacers. So what did the utility do? They said, okay, we finally believe you. You can't use porcelain insulators. So instead of changing them out to poly insulators, they simply stripped back the insulation at all interfaces between the covered cable and the porcelain insulator. So the cost-benefit ramifications of stripping at the interface on the first day was that the cost of the lineman's time to do all this stripping was much greater than the small price delta between a poly and a porcelain insulator. They could have just changed the insulator. The first operational ramification of stripping at that interface is that stripping at every pole essentially converts it to a bare wire system. Why pay a premium for a high reliability covered wire system and defeat all intended benefits by converting it to a bare wire system at every pole? It just didn't make sense. The second operational ramification of stripping at that interface is that now I created a junction or a transition point between covered conductor and bare wire. Okay, any transition is going to require an arrestor, the same as I'm using an arrestor at a riser pole, the transition between bare wire and underground cable. So the stripped location now becomes a burn down site, and it's not practical to install 3 lightning arrestors at each pole. So how did utilities deal with that? Well, somebody came up with what's called a sacrificial anode. And sacrificial anode is essentially a conductor, is essentially a lower melting point blob of zinc mixed in with aluminum installed on a connector at the location where the insulation has been stripped. The purpose was so that when a lightning surge passes by the junction of the bare to the covered wire at that insulator point, the energy which becomes concentrated at this junction then is absorbed by the lower melting point material. Unfortunately, if the location sees a few lightning strikes or maybe a single high energy strike, there's so much sacrificial anode burn that there's none left remaining for the next lightning event. So result is eventually I'm going to have a burn down. So the strategy of a covered conductor stripped at every pole wastes money on labor, imposes extra material costs for dysfunctional sacrificial anodes, suffers a loss of reliability from temporary faults and burn down, loses the advantage of compact construction, is prone to premature failure and loss of useful service life, and essentially converts a covered wire system into a bare wire system. Quick one is, well, you know, how about the covering of taps and the 24-inch separation rule? Okay, this one's simple. Taps should be a minimum 24 inches from each other, and taps should be a minimum 24 inches from the mounting bracket. So you can see in this drawing that's in the catalog, those taps are 24 inches from each other and 24 inches from the pole, or should I say the mounting bracket. And when I do that, I can either insulate that tap, no problem, or leave that tap bare. I might need to leave it back since I'm using a stirrup, right? So I'm going to stagger the taps 24 inches. I'm going to install line duct over the messenger, and I'm going to install a lightning arrestor to protect against lightning. You've probably got a LA anyway because you've got a transformer there. What happens if lightning protection is not adequate? We have lightning protection recommendations in the catalog. Essentially, I'm going to use a grounded messenger every 500 feet or less at all tap locations, junctions between spacer cable and bare wire, underground cable or tree wire, and at dead ends. And if it's inadequate, if lightning protection is inadequate, you know, it depends. You might not need it. It depends on how big the strike is. In worst case, you can get a burn down. But what leads to higher probability of a puncture during a strike is if you have poor insulation integrity, if that cable has been missized, if you're using a 15 kV cable at 25 kV, et cetera, or if the insulation has been degraded due to using porcelain insulators or porcelain spacers. Here's an interesting question. Let's say, well, I'm using spacer cable in a very heavily treed area. How do I ensure I never have a large tree come down and break a pole? Good question. The short answer is there's always going to be something big enough, something bad enough to break a pole, period. 747 hits that pole, it's going to break. Better answer is employ robust design practices. Harden that design further with a flex bracket. A flex bracket is something we came out with that the bracket is designed to spring action. The spring absorbs the kinetic energy of a tree fall at the end of the downward arc. Enough energy has been absorbed by that bracket that not enough energy is left to result in the pole break. It's absorbing that energy on the downward thrust of that tree hitting the messenger. It's possible that so much energy has been absorbed by the flex bracket that it won't flex back. No, fair enough. It's going to have to be replaced, but then the tree is just going to sit on top of the messenger until a routine or an annual patrol identifies its need for removal. And this is what that flex bracket looks like. How about maintenance? What do I need for long-term reliability? A little bit of tree trimming, periodic, keep the large limbs off the trees, keep the foliage off the phases, and keep a couple of spare parts, messenger, conductor, grips, splices, cable, insulators, a little bit of high wire, and line duct. So I wanted to finish off by saying what's new, what's happening in our industry, what are we doing to meet continual need for innovation. We talked about the flex bracket. I can tell you that the flex bracket will save your pole. The tree is going to come down. It's not going to save 100% of your poles, but will save probably the vast majority. This has worked really well. Tree Alert. This is a product that we've just come out with. Basically, it's a little something that you snap onto the messenger with reliability at the forefront of our utility focus. This is going to allow our customers to more efficiently and cost-effectively monitor and manage their spacer cable infrastructure. It's going to provide an accurate record of not only prevented but preventable outages, and it's going to allow you to put a value on that, on what you saved, both with prevented and preventable outages. So that's exciting. And this saved the best for last. Insulation piercing connectors. We've had this at low voltage. This has been around for years, but we've never used it at medium voltage in the U.S. until a couple of years ago. We waited for all the type tests to be passed, and I can tell you personally, I witnessed these type tests that this is the best thing since sliced bread. There's no cable stripping required, no risk of damaged cable strands, no risk of not having the right tool, no risk of a lineman cutting his hand, avoid the time-consuming step of stripping. It's watertight. They're going to bring continuous improvements in the ease of installation, safety, and reliability to the covered conductor arena. And there's a whole bunch of articles out that show you. And we will have information on this ourselves. And what I'm going to do is thank you and for the moment and hand this back to our moderator, Michael Albrecht, to lead the Q&A section.
All right, excellent, Brian. Thank you for an illuminating presentation. A few of you have already submitted questions, so we're going to jump right in. Please note while our presenters are answering your questions, while Brian's answering your questions, please take a moment to complete the feedback form that appears at the bottom of your screen. So on to question 1 here. Brian, is the surface current continuously present all the time?
It's available all the time. It doesn't necessarily have to be on the surface, but when you touch the surface or something touches the surface, it will be available.
Okay. Related to that, what is the maximum surface current in each phase?
Excellent. The maximum surface current in each phase is going to be the same. There is a graph that gives you the maximum surface current for each conductor size for each kV rating. Now, say if I'm at 15 kV and I have a number 2 conductor, that surface current might be, 0.2 milliamps. But if I have a 795 or 1192 kc mil conductor, that surface current could be 2 or 3 times that, well, twice it anyway. So if I have a greater surface area, there's more ability for wet leaves wrapping around that conductor to contact current. So it's actually milliamps per foot.
Okay, excellent. Thank you.
But if that question is submitted, we'll be able to answer it technically with hard data.
Okay, great. Next question then, based on your experience, what is the most aggressive ecosystem in which Hendrix has installed these spacers? The most aggressive ecosystem.
Yeah, I would guess, the most, for me, in my mind, I'd say there might be, I'd have to think about this. I would say the most tropical climates that we have looked at have been, would say Central America, the Pacific Coast, where I have super high humidity, super high salt concentration, and contaminants in the sand, in the silica. And the other one would be the Central Coast, the dry coast of Pacific, South America, that would be Chile.
Okay.
As far as wet or cold or anything like that, that's a piece of cake. Those are not aggressive at all.
Okay, good. Thank you. How about the expansion and contraction of the layers and the DLAM between jackets?
Yeah, good question. The expansion and contraction that we have in a covered conductor system is mostly going to take place with the aluminum at the core, and the polyethylene is going to easily expand and contract that tiny amount with the aluminum because it's much more pliable than that aluminum. And certainly as it as it gets hot, it has a lot more ability to expand. And this would be more something that I would be able to prove out with a UV inhibition type test through aged and unaged samples given the T&Es. But we can again submit technical data on this should anybody be interested in a further clarification of this issue.
Okay, great, thanks. Next question, is there any concern with insulation degrading over time due to abrasion of the tree contact and possibly resulting in energized trees?
Yes and no. Okay, yes and no. So first, let's go to the first part of that. We're allowing intermittent contact between leaves and the spacer cable system for the life of the system. So I have leaves or wet leaves slapping against the conductor. That's no big deal. If I start having tree branches that might have a 3, 4, 5-inch diameter and they have some heft or some weight to them and they're rubbing continuously against that insulation, then yes, there will eventually be abrasion. There's no other result to be expected than abrasion. So as I reduce the insulation wall, I will have, by definition, more surface current available. And eventually, yes, I could, it wouldn't so much energize that tree unless that tree was completely wet. We've seen complete contact for years and never, quote unquote, energize the tree. But theoretically, could that cause a problem if I had fat tree branches rubbing on that tree for years? Yes, it could cause a problem.
Okay, great. Thanks, Brian. Next question, can you talk about how the spacers are typically installed as the conductor is strung or after stringing and tensioning the conductor with a bucket truck?
Yeah. We have an installation method called the roll-by method. Basically, you pull in your messenger, you tension the messenger 2,000 pounds at 60 degrees Fahrenheit, and then you pull in your three-phase conductors with roll-by stringing blocks that are spaced evenly every 30 feet. I go and I sag. I dead end those phase conductors at the far end. I go to the payout end. I sag the conductors such that I have 6 inches of phase conductor sag every 30 feet. Then I put my phase conductors at the payout pole into my dead end grips. Now I'm completely dead ended. Now I just roll down the street in the bucket truck and take off the roll-by block every 30 feet and replace it with a spacer until I've reached the far end.
Okay, great.
We have installation instructions that spell this out, and also a complete service department of installation specialists that regularly work with utility clients to get this done. Okay, great. Thank you. Next question, are there limitations with a severe ice load? There's no limitation on the system. There's certainly limitations on the poles. So when we're designing a system, whether we design that system here with whatever PLS CAD, or we're working with the utility with one of their loading programs or PLS CAD, basically they're designing it just like a bare wire line. They're going into their NESC regions or their CSA regions or whatever loading conditions they have, whether that's 0 degrees Fahrenheit and 3/4 of an inch ice and 60-mile-an-hour wind. We model the system and we see what safety factor we have in the pole. So again, there's no limitation on the system. The limitation is going to be on the pole, and that's why we take a look at the poles when we design these systems. And also, that goes into defining which messenger we use, the rated tensile strength of the messenger. Okay, great. Next question: how do you recommend dead ending this conductor? Simple. We recommend deading it in preformed conductor grips that are neoprene coated. They're very long, and obviously there's no tension on these phase conductors, maybe 100, 200, 300 pounds, depending upon what it is. So it's no problem putting them in partial tension preformed dead end grips. There are other options, stripping it and putting it into full tension dead end shoes, but that's a waste. Again, you're stripping, you're using dead end shoes, you're converting it to a bare wire system. Just a pain in the neck. Use the right grips, and life is simple. You can keep it compact.
Okay, great. Thanks. Can you speak about the need to keep trees trimmed so that the spacer cable does not have an insulation failure due to long-term voltage stress?
Yeah, I mean, sure. Again, that's part of the maintenance program. You're going to have to do periodic tree trimming. You're going to allow intermittent contact, but you don't want temporary contact. You don't want permanent contact, and the more you have permanent contact, the bigger those limbs are getting. I mean, if you've waited to do tree trimming until you've got a 6-inch limb sitting on the cable, you probably have held off tree trimming too long. Hopefully that limb is sitting on the messenger, in which case you don't have a problem at all. Utilities have told us that they're saving 80% of the tree trimming, number one, and number two, they're doubling the cycle. So if they have, a two-year cycle for bare wire, they're tree trimming spacer cable every 4 years. And some of our tropical clients, whether that's Panama City or Brazil, they have 12-month tree trimming, so they're spacing that out to 24 months now with the spacer cable.
Okay, great, thanks. Can you describe a typical application, Brian, and should it be installed in urban environments?
Yeah, sure. In urban environments, what we have is we have space limitations. So we're going down a city boulevard where we're close to 3, 4, 5, 6-story buildings. So I'm able to get close to those buildings without requiring that 7.5-foot space. And secondly, I'm not creating a safety hazard because there are people around those buildings, maybe people working on the roofs, maybe people working on signage, maybe people working on, the traffic lights. Secondly, you will see a lot of the municipals here in the Northeast. They're using spacer cable because they have double or triple circuits down the main feeder line substation exit. They're also having their telephone wires or their cable wires on those same poles. And to do that with bare wire would, number one, be impossible on that same pole line. And number two, even if they did it, would be vastly unsafe because to work on one line, you have to de-energize the whole darn thing, de-energize the whole metro area. And I could probably think of other applications if you gave me time, Mike.
Okay, great. Thank you, Brian. Next question is, I've seen a tie wire cause the largest number of failures on bundled conductors. How has this been addressed with tie wire?
With bare wire and covered conductor, I'd best have that one submitted in writing and give me a time to answer that. How has it been addressed? We basically introduced covered tie wire. We've always had covered tie wire. It's simple to use. Just don't use bare wire. And the second way that problem has been addressed is that utilities have simply gone to the vice top insulator. They don't have to worry about any tie wire anymore ever again. The covered conductor goes in the vice top. They turn the screws and they're done.
Okay, excellent. What's the comparable cost ratio to equivalent ASCR conductor?
Yeah, okay. We're saying that at 15 kV, a spacer cable is probably going to be a 15 to 25% premium over bare wire. At 25 kV, it's going to be a little bit more than 25%. At 35 kV, it's going to be even more than 25 kV. But again, if you can use bare wire, you don't need spacer cable. You're only using spacer cable when you have issues with reliability, when you have issues with severe weather, when you have issues with tree-related applications, when you have issues you want to use multiple circuits, tight right-of-ways, underbuilds, renewable energy, these types of things, storm hardening, fire mitigation.
Okay, great, Brian. Well, I'm afraid we've run out of time. Thank you for your answers and all your questions. I'd like to thank Brian Trager for his outstanding presentation and our sponsor, Marmon Utility. Thank you all and have a productive remainder of the day.